This image shows an overview of an experiment called titration. This over here on top, that is burette, and in that burette is an unknown concentration base, meaning I don't know the base molarity in there. In here is an acid, but we know the concentration, known concentration of the acid. And also in that same solution is an indicator. The indicator will help us to determine when the base and the acid are equal in mole-to-mole ratio, whereas this whole entire solution is neutral. So what I'm going to do in this experiment is to open up this dial and then allow the sodium hydroxide to fall through, if it's sodium hydroxide, so some kind of base to fall through. And once the base salt falls through, we stop at a point where in which the solution turns slight pink. And that's where the indicator comes in. The indicator is the one that says, hey, don't put any more base in because you're neutral now, okay? Unless you're trying to go over. Now, so the indicator is only there to help us see visually when it goes into that mode where it's entirely neutral. If the indicator is not there, it will remain clear and we don't know when it becomes neutral. Again, this whole entire experiment is called the titration. And the titration, by definition, is adding the unknown concentration substance to a known concentration substance. And you actually get to know how much in volume of the unknown it gets submitted in there. What is the whole purpose of doing this? Just to get that neutral substance? Not exactly. It's so that to find out what is the concentration of this. Okay, so the whole purpose is to find that unknown concentration. This is a problem that is based off of titration. Now, there are a lot of words in here, so I'm going to go ahead and split the view so that you can see this problem and also the experiment of titration side to side. So it says a student carries out a titration to find the concentration of sodium hydroxide solution. To do this, the student weighs out 1.3009 gram sample of potassium hydrogen phthalate. Now, potassium hydrogen phthalate is KHCH404. Now, this is a handful name, so therefore it's abbreviated as KHP. KHP does not mean it has a potassium hydrogen phosphate in it. It's just an abbreviation of this entire molecule. And also gives you the molar mass of KHP, which is 204.22 grams per mole. So what in this experiment it's saying is, I'm going to take this weighing boat here and I'm going to put it on top of the scale, as you see over here. And I'm going to weigh, what was it again? 1.3009 grams of it. That's what it's saying. Okay, so I have some KHP here. Now, KHP is the acid. Okay, that's the acid. Now, because you're weighing that out, this must be a solid. It's solid, so not in a solution yet, and we're about to make a solution. Then the student dissolves the KHP in distilled water. So we're going to put this KHP into this flask over here. Then we're going to add some distilled water over here. Okay, so it's mixed. I'm going to leave my weighing bowl here. So now I have KHP solid and water and mix them into a solution. Then add phenolphthalein as an indicator. So this is a phenolphthalein. I'm going to add a few drops in there as an indicator. That's the one that's going to allow the solution to turn pink when it's neutralized. So I used this already, so I'm going to leave that to the side. And titrates the resulting solution with the sodium hydroxide solution to the phenolphthalein endpoint. What that means is I'm going to put this under this burette over here. This burette is going to contain sodium hydroxide already, but we do not know what the concentration is. Okay, we don't know what the concentration is. And you're going to titrate it, meaning that we're going to allow the sodium hydroxide to flow through this into this flask. Okay. Now, how much did you put in? Well, it tells you right here. The experiment indicated 0.04120 liter of sodium hydroxide was required. Okay, that was required to react exactly with that KHP in there. So here's my sodium hydroxide liter. Here's my KHP solution. You made that by putting the powder in and the water mixed together, right? But you use 0.04120 liters of the sodium hydroxide. Now it's asking for calculate the concentration of sodium hydroxide solution. Okay. Now so I hope you have an idea of what's going on. So we put this base in here, but we don't know the concentration. It's asking for what is the concentration here. And we treat this like the acid and base stoichiometry problem. Number 1, get the balance equation. Number 2, figure out the starting point, and the starting point is the reactant with the most information. And then we want to end with whatever you're looking for, the unit that you're looking for. And number 3, set up everything in between. Now, if you don't know what I'm talking about, then you haven't seen part 2 of this video. So I'm going to go in that same step order. Now, I already have the equation and it's already balanced. So I don't need to do that first step. Second step is to find out what information do you have regarding the reactant, okay? And the most information about it. So our information is either based off of sodium hydroxide, the base, or the KHP. If you look in this particular problem, it gives you more information about KHP than sodium hydroxide. It gives you the mass of KHP, molar mass of KHP. And then for sodium hydroxide, it gives you just the liter. Okay, so I'm going to start off with the KHP information. And that would be 1.3009 grams of KHP. And the end is what I'm looking for is the molarity, right? I want to know the concentration. Molarity is moles of NaOH over liters of NaOH. This is same as molarity, but I put it in a split form. So we're trying to get from the grams of KHP all the way to molarity. Let's see if we could do this. It gives you the molar mass of KHP, which will help us to cancel out the grams of KHP. So this is my third step where we put all of these guys together, grams of KHP. And that's every 1 mole of KHP. By the way, this is the KHP. Now, somehow we need moles of NaOH, right? We need the NaOH, so somehow we need to switch that so we get the mole to mole ratio in this balance equation. So since it's 1-to-1 ratio, we will write every 1 mole of KHP. There are 1 mole, well, there is 1 mole of 1 NaOH. Okay. So far we can cancel out the following: the grams of KHP, the moles of KHP. Okay. Right now we have moles of NaOH. which is good. So because we want that moles of NaOH to be on top of that. And now we want to know liter. We need to have some kind of liter on the bottom. And we do have that liter, 0.04120 liters of sodium hydroxide. So let's go ahead and put that on the bottom. Zero point 0.04120 liters of NaOH. So we have everything there. And so what do we put on top? Well, that we just put 1. That's okay. And so we can cancel out all the units, unnecessary units, and left with the units that we really need, which is moles and liter on the bottom. Take out your calculator and let's calculate this out. So 1.0309 times 1 times 1 times 1. Okay, so that's all of these things on top. Enter, and then going to divide that by everything in the bottom. That's 204.22 times 1 times 0.04120 liters on the bottom, then parentheses. That will give me 0.155. We need to have 1, 2, 3, 4, 5 sig figs. Okay, 5 sig figs. Oh, actually, you know what? There's only 4 sig figs on this liter, so 4 sig figs. So 1546. Or you could write this as 0.1546 molarity of NaOH. So either one would work in terms of your final answer. Now you might be wondering, well, my instructor did not give me more information about this. In fact, it didn't give me the molar mass. It gave me this. Well, if that's the scenario where you don't know, like it only gives you one information about one thing and only one information about the other, think about what you're looking for. If you're looking for sodium hydroxide solution, right? That's what should be in the end. Most likely that setup, that utilizing that particular number will become towards the end of these train track, if you will. If this is a whole train, this is towards the last track, and the other one will come in the front. That's kind of like how you can visualize which order, which one goes first and next, is by looking at, well, which one is talking about at the end. And we're talking about sodium hydroxide at the end, so therefore I put the sodium hydroxide information at the end. The other one left over will be the KHP. This is a similar problem as the titration and the previous one. Try this and come back and check the key. And here is the key.